Yes, so recording has started. Okay, welcome once again to this today's lecture. So in the last class, okay, before we start this today's new topic, which is actually a continuation of this capacitance, MOSFET capacitance only, right? But let me just briefly, recap the things that we have done last week. So in the last week, we have started a new topic, which is the capacitance in a MOSFET. But so far capacitance means we have studied only the gate capacitance, right? But we have also seen there are other parasitic capacitances as well, other than this gate capacitance. Gate capacitance is quite easy, like it is CF epsilon ox by Tox, right? It is the per unit area capacitance. But we have also seen due to this MOSFET fabrication, like by say particular technology, there will be an overlap of this gate uh, between gate and source as well as between gate and drain. So that will result in a overlap capacitance. And as the MOSFET is a symmetric device, so we know that these two capacitance, overlap capacitance would be actually equal, and it would be represented by this value. And from here, we can clearly see that these capacitances, this overlap capacitances would be a parameter as a design parameter as well. Means it depends on your design because it is directly proportional with W, right? So W is coming here. So you can clearly see that it is dependent on the value of width, right? Which is a design parameter, right? So yeah, this is the maximum value, minimum value that what we have calculated, means the type of discussed here. I think this is small recap. So if you have missed last class lecture, I strongly encourage you to please go through that lecture because that is very much important, okay, for understanding the consecutive classes. Then after that, regarding we have started our discussion on this channel capacitances. So in regarding channel capacitances, we have seen that channel capacitance maximum would be basically the gate capacitance, right? It is basically the gate capacitance maximum value, right? But we have seen that depending on the region of operations, means whether the transistor is in cutoff, triode, or in saturation, we have seen that this capacitance can be divided into three parts. One is this gate to source, means this gate to channel capacitance can be divided three parts: gate to channel for the source, gate to channel for this drain, gate to channel for this body. And we have seen this during cutoff, the body capacitance plays the major role, right? During the triode region, the body capacitance, like gate to body capacitance becomes zero, and the total gate capacitance would be equally divided between the source and drain. Whereas when it is in the saturation, there will be a the this region will be now somewhere disconnected, okay, from this drain terminal, and as a result the entire capacitance would be shifted from the gate to channel capacitance would be shifted from this. Earlier you have seen that it has been equally divided, but now the total thing would be shifted to this side, right? Gate to source. And we have seen this value will also reduce slightly, like its value compared to the earlier cases would be reduced by 1/3, right? So the actual value become 2/3 of the CGC. Right. Then we have also seen that if we are plotting for a particular VDS, that is VDS equal to 0, then how does this three individual component would look like, as well as the total capacitance, right? I hope that you have understood it. If you have any doubt, you can ask. Like uh, then we have also seen here that in other case, here we have kept VDS equal to 0. We are changing only the gate voltage, and here we are changing this gate drain voltage as well. And we have seen that how for depending on the region of operation, the total capacitance as well as gate to source, means gate to source channel capacitance, gate to drain channel capacitance are changing. Right. Then we have concluded with a simplified table, right? This table would be quite handy if you are solving some problem, right? What is the capacitance and which region of operations. So depending, you can take this value and solve that. So if you agree with me on this topic, then probably we can move. Okay, I think we have also covered regarding this junction capacitance, right? So junction capacitance is basically like gate and source, like this drain and source are, these are the diffuse regions, right? And as these are the diffuse regions, so for example, if you're considering this NMOS case, Then for NMOS case, this is basically this N plus region, whereas below that you have this pure silicon region. As a result, you have a depletion layer, and you know the depletion region, whenever there exists a depletion region, there will be incapacitance. So as a the moral of the story is, then you have some capacitance between this drain terminal and body terminal, as well as the source terminal and the body terminal. And we have also seen how these capacitances are dependent on this width and how to calculate it. Okay. Okay. So this was the brief discussion in the last class. So now then, if we have to write what are the total capacitance for an MOS, for an say N channel or P channel, or NMOS and PMOS, NMOS, then what would be how the total capacitance would look like? For example, you can see these are the three terminals, right? Gate, source, drain, as well as here the body terminal is also been shown. So obviously we can see that there will be one capacitance between gate to source, one capacitance between gate to drain, gate to body, right? At the same time, there will be capacitance between source to body, source to this drain, then drain to body as well, right? So if you have to see what are the total capacitances and what are the components of these capacitances, right? Then we have to probably look on this. And I hope that you have, if you have understood the earlier discussions, then these things are pretty easy. For example, let us see this CGS, right? Gate to source capacitance. So see this gate to source capacitance, clearly you know it comprises of two things, two capacitances. One is this CGCS, that is gate to channel, gate to channel capacitance contribution to in the source side, and this gate to source overlap capacitance, right? There cannot be any other capacitances between this gate and source terminal, right? So I hope that you will agree with me on this, that gate to source capacitance would be represented by like this, right? And we individually know what would be the value for different region of operation for this as well as for this. Okay, anyway, CG is not overlap capacitance, is independent of the biasing condition, but the CGS is dependent on the biasing condition, right? Similarly, if you look for the second case, that is CGD, that is this one between this gate to drain, then you can also clearly see that it is nothing but the CGCD and CGD naught, means gate to channel, the contribution towards the drain side, as well as the overlap capacitance between this gate and drain terminal, right? Similarly, what is this GCB, sorry, CGB, that is gate to body capacitance. Then this gate to body capacitance is nothing but the contribution of this gate to channel capacitance, okay, right? And you know that this only plays a role when the transistor is in cutoff. Okay, now I think one of you have asked, I just wanted to clear here that when the transistor is in cutoff, say at Vg equal to 0, then how come it can have a capacitance? So it does not matter what is the DC biasing condition. Okay, even the bias applied is between these two terminal is 0, then also there is the capacitance. Capacitance does exist. Okay, it does not depend what is the DC voltage across that capacitor. Okay. Maybe more discussions we will take tomorrow regarding this. When how these capacitances are measured, means not this, means suppose you have to measure any capacitor, okay, and what is the then log, how do you do that? Okay, then once you understand that, then we will also take the MOS capacitor structure, MOS. Then we will see how to measure this capacitance. Okay, because here normally when we say that this is an suppose discrete capacitor, we connect in multimeter, then how this measurement has been done. But you cannot really do this MOS capacitor here, this measurement using a multimeter. So you have to apply some DC bias. Okay, you have to operate in some DC bias and then measure the capacitance. But it does not mean that when this voltage is 0 here, this capacitance, MOS capacitance is equal to 0. Okay, so we will understand it. I think a bit. We'll discuss some, spend some time on this. Okay, capacitor measurement. Okay, then you can see here we have two more capacitances, that is here CSB. Then definitely this between source and body, the capacitance would be due to the diffusion capacitance, right? As just now we are discussing. between this, suppose from this is the drain terminal. So between drain and body is this below, right? Body is below. So between drain and body, the capacitance would be due to this diffusion region, right? So similarly, from this drain to body, sorry, source to body, the capacitance would be also due to this diffusion, right? So it is pretty clear, like what would be the total capacitance? Any doubt here? Okay, so if no doubt, then let us move to the next part. Next part is the what would be the input capacitance of an a CMOS inverter. So this is the input capacitance of an inverter, CMOS inverter. Hmm. So how do you estimate that? Any idea what would be the input capacitance? So basically we are looking from here and we are seeing what is the total capacitance. Let's see who can tell me. Yeah, what about Dikshant? What about Shubhayan?
Sir,
Hmm.
that would depend on which region we are operating, right?
Hmm. So yeah, so can you give me some estimation? Like, yeah, I agree with you.
Yes, so for example, like if we consider uh, like both are in triode or like uh, one is
Is
in
it
cutoff
possible?
and one
Is it
no sir,
possible
no sir,
that
no
both
sir.
the
Actually,
transistors?
that was an impossible case. Like one is in cutoff, one is in saturation. We can consider that.
Yes. So, Arsh,
Yeah.
is it initially you mentioned that it might possible that both the transistors are in triode. So, is it possible for a CMOS inverter?
No, sir, I don't think so. Actually, I didn't do a detailed analysis, but I don't think it's possible. I just like it, just threw it in the air. I just wanted to consider a single case, and I just said it by chance. I don't
Okay.
think it's possible.
It's not possible, right? Because
Yeah.
we have seen that, right? Region of operation. So, it's not possible that both transistors are in triode for a
Yes.
CMOS inverter, right?
So that we can
So,
consider one saturation, one cutoff, then it is possible. So
right,
like for cutoff, there will be a major part from the gate body capacitance for one of the cutoff transistor, and for the saturation part, we will have only the like the drain to body and source to body.
right, right.
Yeah,
So, what would
all
be,
of that
so
would be
what do you
added.
think? Then, what would be the total capacitance?
So like if we consider both of the transistors to be identical in terms of construction, you can say that it would be CGB plus CDB plus CSB.
CDB, CDB.
So
Okay,
like
please tell
drain
me.
body plus source body plus gate body.
Drain body. Okay,
Yes, sir.
drain body, source
Plus
body,
source body plus gate body.
plus gate body.
Yes, sir. For the
Gate,
cutoff one, there would be
gate body.
gate body, and
Okay,
for the other one would be
right, right, right. But may I know why you are considering, yeah, gate body I can understand, but may
yes,
I
sir.
know why you are considering this too?
The saturation region.
Yeah, what is dB? Say, I am again plotting here this NMOS. So what is dB here? Say this is drain, this is gate, this is source. So what is dB?
So actually, in this part, we don't consider a body, right? Yeah,
No,
it's
no.
like
Now I am I have
plotted.
plotted this body. Yeah. Now
Sir,
tell me what is dB.
instead of the dB, should there be CGS into C? I mean CGD into CDB divided by CGD plus
Right, right,
CDB.
Shubhayan. Yeah,
And
right,
for
right,
AC
right,
also that.
right. So, Arsh, please try to understand. Like you are saying this dB, right? So dB is basically this, right? So is it associated with this gate, right? This is between this drain terminal and body terminal, right? It is not
Oh,
between
yes, sir. Yes,
this
sir. Yes, sir.
the
I
gate,
get
right?
it
But
now.
we are
Yeah.
considering here the input. So definitely
Yes,
this
sir. Yes, sir.
capacitance would not come, right?
So like it would not be part of our current flow circuit, right?
Right.
Circuit
So,
that we're actually considering.
hmm. So if you are considering the input capacitance, definitely this would not come, but this would come, right? Yeah. Shubhayan, you are saying something. Could you please repeat? Shubhayan?
Yes, sir. I was just saying that
Uh,
instead of that dB, it should be CGD into CDB divided by CGD plus CDB
CGD,
into
CGD. Okay, and
CDB into CDB.
CDB. Okay.
Yeah, divided
So
divided
okay,
by C.
why this DB is coming again? Like I think I discussed like why DB should not be there. Why do you think this DB should come here?
So basically, in from the previous page picture, I was just imagining that to be
Uh-huh.
a simple circuitry.
Hmm.
Yeah, this is to be a simple circuitry where we have one point at G and one point at B,
Right. But
and
see,
this is
see this DB is this one, right? But
yes,
DB is not, but this capacitance is not connected with this, right, gate,
yes,
right? So, okay, but rather, if I say it like this capacitance would be the input capacitance, if I look from here, would be the capacitance which are actually connected with the gate terminal, right? For example, this GS, GD,
okay.
isn't it?
Yeah, but sir, S and D are not in. I mean, their voltage differs, right?
Their voltage differs.
So it should not be a direct CGB plus CGS plus CGD. It should be something else.
Why not?
So it is not a direct parallel connection,
Uh,
right?
when you are considering, suppose the like what is the equivalent capacitance, right? It does it matter that what is the capacitance like and what is the voltage between this terminal and this terminal and this terminal and this terminal?
No, that does not matter. But I was just saying that it is not a direct parallel connection.
Yeah, then why not it is a direct parallel connection? If the DC value does not matter, right? Then like this and this are in parallel.
So can we not say that CGD and CDB are in series?
Why?
Yes, sir.
How
I was
can
just thinking the same thing.
CGD and
CGD and
See,
CDB.
CDB are in series. Okay. Please explain why. How can you say that these two are in series?
So because so both of them are connected to D at one point.
But both of them are connected to D. But this D is at fixed at some DC bias, right? Are you not getting my point?
Yes,
This
sir,
is
yes, sir.
connected with some DC voltage. Okay. And for AC analysis, what do you do? This DC
Uh,
voltage,
yes, sir. Yes, sir.
you short it,
okay.
right?
Yes, yes,
Yes,
sir.
sir. Yes,
Oh,
yes, sir.
yeah.
So when
Got
you
it.
consider this, then like this point and this point, are these two, are they not in parallel?
Yes. Yes.
Yes, sir. Very
That was, yeah.
Okay. So then definitely we can say from here the total capacitance would be the capacitances, okay, which are actually directly connected with the both of these both gates, right? For N channel and P channel, right? Now the question is, okay, then let me write it here. The total capacitance, total capacitance CG would be equal to CGCN, right? Gate to channel capacitance. I'm not dividing it. I'm writing the total gate to channel. Okay, not three components. Gate to channel capacitance plus gate to channel capacitance for N, gate to channel capacitance for P plus what else I should write if I consider the total gate capacitance? Am I missing something here? Any other capacitance other than the channel capacitance? What about the overlap capacitance between this gate and drain and gate and source? Yes, Shubhayan. Should it be there or not?
Yes, so basically it should be CGB plus CGS plus CGD. Now we can replace CGS as CGCS plus CGSO.
Right. So basically, we have to consider this overlap capacitance, right?
Yes,
And you
yes,
know, if this NMOS and PMOS, their widths are different, right? Then the overlap capacitance are also going to be different, right?
yes, yes.
Right. But this overlap capacitance, that is C naught, if I say, this overlap capacitance would be same as this overlap capacitance. because the width is same on the source side and P
Yes,
side,
yes.
source side and the drain side for PMOS. Right? So that way I can definitely say that this component should be there. At the same time, this component should also be there. Please tell me if I'm wrong here. Am I wrong here? Yeah. What about Alisha? Alisha, you are not saying something.
But till now, I was able to follow. It seems okay.
It seems so okay, right? Okay,
Yes,
fine.
sir.
Okay. Then what would be this value? And what would be this value? Yeah, Alisha, you should say it. What would be the value of this and what would be the value of this? Is it constant? First, tell me. Is this CGN constant? Alisha,
Uh, yes, sir.
is it constant? CGN, CGP?
I think
You think? Why do you think it should be constant? What is CGN? You see here. This is this is actually CGC, means CGC, P or CGN.
hmm,
Is this constant? Is this constant here?
yes, sir.
No. Why?
Oh,
How you
sorry,
think
sorry,
it is constant?
sorry. No.
It is not constant, right?
Yes,
So
sorry.
it depend on the region of operation. However, okay, when you are considering the delay, we always try to consider the worst case delay, right? The maximum delay. So the maximum delay is when possible, when the capacitance would be maximum, right? So considering that, we will take this value only. Okay. So
Yes.
okay, when we are considering this worst case delay, so first let me write it. So it would be Cox WNL plus Cox WPL plus here 2 C naught WP plus 2 C naught WN, right? So, and why we are considering this value and this value? Because we are considering the worst case delay, right? For these two. Okay. So just now, I think you can do like little bit represent it like this: WN WP plus 2C naught here WN plus WP. Just a bit simplification, right? So now you know that if suppose, okay, let me put it in this way. Suppose if you have a inverter or an inverter here. If you have an inverter here, okay, then this inverter has to drive the next stage inverter, right? So for that, you should know what is the capacitance, okay, that you are seeing, okay, from here. So that part now we can calculate from here, right? That what would be the capacitance seen by the first inverter if it is driving a next inverter, right? So it is very important how to calculate the input of capacitance of an inverter. I hope this part is clear to you. Now let us see, is there any effect, okay, of this capacitance? Because we have seen there are so many capacitances associated here, right? So does that mean, right, that this any of the capacitance will also contribute as an output capacitance for this inverter? That means, is there any self-loading effect? Okay, in other words, is any of the capacitor which are actually connected, are they connected at this output, or are any of this capacitor is influencing the transient behavior of this inverter, means of this transistor or not? So let us see that in the next page. So that part is called self capacitance. Okay. So here, before we start, what is to discussion this regarding the self capacitance? Let us first understand what is the self capacitance. So self capacitance is the sum of capacitances connected to the output V out. So still see here, if you consider this inverter, we have not connected anything, means any load at so far with this V out, right? Now we have to see, okay, what are the capacitances associated, okay, or connected with this V out terminal. So that means this first stage inverter only loading itself, right? Some load is coming, capacitive load is coming because of this driver inverter only, right? So let me write that here as well. Self capacitance is the sum of capacitances connected to the output terminal, that is connected with this V out. Okay. Now, if I can tell this much, I want some help from your side. So here I have, you can see, I have drawn for this inverter almost all the capacitances which might be possible. Okay. Now you have to tell me how should I approach for finding this self capacitance. Anyone, but quickly. Let's see who can answer this, or means who can comment on this.
CSDP plus CDBP plus
Uh,
CDB.
Shubhayan, your voice is not very clear. Could you please repeat?
Well, sir, I think here CDBP and CSDP they are in
CDBP and CSDP.
SDP. Yeah,
Okay,
they are in series,
they are in series. Okay, this is
and
your comment. Okay.
in the other side CDBN and CSBN they are in series, and these two series are parallel.
Uh, okay, these two are in parallel. Okay, but Shubhayan, I have a question here. Right, like for this configuration, I think I have drawn this body terminal as well, right? And you know, for NMOS, the body terminal is connected in general. Okay, if you are not using the body terminal is been grounded, right? So body terminal is grounded here, and for PMOS, the body is generally shorted. Means both body and source are shorted, right? So that way for
Okay,
PMOS.
then we don't need the SBP and SBN.
Very good, right? Then obviously you can see this port and this node are been actually connected, right? So the capacitance between these two we should also not consider. Isn't it right,
So,
Shubhayan?
Yes, sir. Yes.
Right.
hello, sir.
Huh.
So, in previous case, why we were considering the drain, like in previous case, can you shift a bit,
Yeah,
sir?
sure, sure. This one, na?
Yes, sir. So, V out isn't connected to the like any DC wires, right?
V out is not been connected with some DC bias.
So why we were considering suppose in the PMOS,
Hmm.
G and D. So channel capacitance from G and D as parallel to that in case of NMOS.
Channel capacitance of between G and D. So between this, you were saying
Yes, sir.
this capacitance is in parallel
With that of PMOS.
that of PMOS. Okay. Anyone would like to answer?
For AC analysis, the DC value should be and we need
Right,
to that's why we
right,
out.
right. So when see if we are now considering it as in a standalone inverter, but if you consider it in a circuit, so is this terminal is floating? It's not, right? It's not
Okay,
floating.
got it. Like in general, we like connect something, so we consider it as grounded in this case.
Sure. Okay, so I hope this part is clear to all of you that why you should not consider this. Okay, and
Sir,
definitely, yeah.
sir, can you please once again tell why CDBP and CDBN are in the current path, or why are they being considered?
For this case or the previous case?
No, sir, exactly this case,
Oh,
the
this
thing
case.
that is on screen.
Right, right.
Yeah.
Why this?
Sir, CDBP and
Uh-huh.
CDBN are being considered.
Why they are considered? Because you see, we are now interested to see what are the capacitances which are now associated with this V out or connected with this V out. So you can see this V out, okay, this terminal means V out is connected with one terminal is connected with this, other terminal connected with the DC. For this V out, this terminal is connected with this capacitance and the other terminal is connected with the ground, means basically in fixed voltage. So that is the reason why we are considering like this one and this one associated as a associated capacitor with this V out.
Okay, sir.
Okay.
Got it.
Okay.
Yes, sir.
Yeah. Okay. So let us. So you have understood regarding these capacitances, like which are connected with this output side. So do you think that these capacitance would also play a role? For example, which the capacitance I have drawn using this green color. CGSP, CGDP, CGDN, CGSN. What about these capacitances?
C, GDP and GDN will contribute.
Yeah, so you can see that CGDP, CGDP and CGDN, they are at least one terminal is connected with the output. So definitely these two are going to play a role, right? Right? Okay, while calculating the self capacitance. Okay, do you think that CGSP and CGSN would be contributing? No, right? Because they are not actually connected with this output node. So again here, these two are crossed, right? So then if we type of simplify and okay, and while we are considering this, okay, to make our calculation bit simple, we are considering that the input is an step input, okay? So if you consider the step input, that helps basically, then one of the transistor is in the cutoff and the other transistor is means most of the region actually if you see that for during if you consider like VTC of and this, then during most of the region, right, one transistor would be, I mean, the both the transistor would be either in the cutoff or in the saturation region, right? The linear region would be pretty small, right, for a good inverter. Means the linear region of operation, I'm saying, the linear region of operation would be very small, or the triode region would be region of operation would be very small. So that way, it's basically it would be easier for us because it is only the cutoff or in the saturation. Okay, so if you consider this for all these capacitances and we have neglected some of them and considered some of them, right, with some justification. So probably we can simplify this diagram like this. So we have associated capacitances with this four, right? Okay. Now, could you please comment one, what about this CGDP? What would be this capacitor? What is this CGDP and what is this CGDN? These are what capacitances? Diffusion, overlap, what? Quickly.
Sir,
Who can
overlap.
say this? It's obviously the overlap capacitance, right? So it is overlap capacitance. So you can see here this CGDP. So actually CGDP, then I can probably also write here CGD not P, CGD not N, because these are the overlap capacitance only. And CGD not, we know that we can write it like this, and CGDOP, because these are proportional with the width of this NMOS and PMOS, right? And if we see the these two terminals shorted, these two terminals shorted, they are parallel. So obviously the resultant capacitance because of these two, right? Because of these two, resultant capacitance can be written as this is nothing but the summation of these two. So which is basically this one. right? Now we are representing the resultant capacitance by the CGD naught. Okay. So now see, let us know, for the time being, not consider these two, okay, like CGDB and CGDB, because we know that these two capacitance would be there. Let us now try to focus only this CGD naught, right? So if you consider the CGD naught, which is basically because of these two, right? Then you see these two terminal is been connected here, like. And now if you consider the input output relation for this capacitor, then you can see when the input side changes like by delta V, then the output, because it is an inverter, will change by minus delta V, right? Then what is the resultant change? What is the resultant change between this input and output, or between the two terminals of this capacitor, right? Resultant change. What is the resultant change? It is delta V. So it is basically minus delta V, right? Minus of this delta V. So it is basically 2 delta V, right? So from that, I know it's basically type of, we are doing such type of, Miller capacitance analysis. So from here, we can say like, because this type of capacitance where both terminals are type of, connected between input output, a bit easy, bit difficult for us to go calculate, or, do our hand calculation. So to do our hand calculation bit simpler, what we can say then, that is, as this total voltage across these two capacitors are changing by 2V times, like 2 delta V times, then we can also say it would be equivalent if we consider a capacitance of twice this value, and one terminal is connected with this, and the other terminal we can say is been connected with yeah, with ground. Because here you can see, if you now change it this V, right? If you consider, because this capacitance has increased 2 times, so the resultant effect becomes the same. Please let me know if this is clear to you.
So what is the C naught in the formula you wrote above?
C naught.
C naught into Wn plus Wp.
Oh, C naught. Okay. C naught is the overlap capacitance per unit width.
So why is there no channel capacitance?
Overlap capacitance per width. Why there will be not be any channel capacitance?
Gate channel capacitance.
Gate channel capacitance. So, okay, that is a very good question. Can anyone answer? A very, very good question. I think I have missed this point. So why it should be this, why, okay, let me write this question. That would very good that you have asked. Why CGDP, no, GDP and GDN, okay, should consist of only overlap capacitance. So this is important questions. Yeah. Please think and then tell me why there should not be any channel capacitance.
There should be no gate to drain ones because we know
Yes,
one of them is
yes,
cutoff region.
yes, Alicia. Very good, very good. Because see, like these two capacitances are between gate and drain, as well as between gate and drain. As I mentioned, like for most of the region, the transistor is either in cutoff or in saturation. So both either in cutoff or in saturation, that this gate to channel component associated with the drain side become equal to 0. Right?
Yes.
Because transistors are in saturation or cutoff, so both in saturation and in cutoff, C, G, C, D, right? As well as here too, C, G, C, D, like both would be almost equal to 0. Right. So that is the reason why this two will only consist of the this overlap capacitance. Right? Okay. So if this is clear to you, then could you please help me in writing this, then what is the this C self? This means the self-loading capacitance. C self. What would be the total self-loading capacitance? So here we have seen it is basically 2 times of CGD naught, right? So then definitely we can add here 2. So it is 2 C naught, then Wn plus Wp. What else? What about these two? What is this capacitance? This is due to. Hey, tell me quickly. I need to go next.
So junction
The
capacitance.
diffusion.
This is junction capacitance, right?
Diffusion.
So both are junction capacitance, right? So CGDP and these are the junction capacitance, right? So here let me write here. These are the junction caps. Here also this junction cap, right? So here it is CJN, then WN plus CJPWP. And here remember one thing, we cannot actually make this both like CJ, because the junction capacitance for N channel depending on the doping it might be different compared to in the P channel. Okay, so these two would be different, right? So you know now from this analysis that if whenever you are considering an inverter, some capacitances which are inherent of this like inverter only, they will also be associated at this or connected with this output terminal. That means those capacitance will load this inverter itself, right? So it's not only the output load this inverter have to drive. Okay, when you connect an inverter, this inverter will load itself. And see one thing, suppose if you want if you have some inverter, okay, and and you want to drive a load, capacitive load, okay. If the load is more, then you need higher current. Means to drive it first, you need higher current. So to get higher current, what you will do? You will increase the size of these transistors, right? But see here, when you increase the size of this inverter, that means Wn and Wp will increase. At the same time, you are also increasing your C self. That means you are also contributing more self capacitance in that process, right? So it does not that way like 1:1. Okay, you have load capacitance higher, so just increase the previous inverter. Okay, it will solve the problem. No, it's not like that, because that will also going to contribute some additional capacitances, right? As you have seen here. I hope this part is clear to you.
Hello, sir.
Hmm.
Sir, in this case, we have considered the variation in both input and output voltages for calculating the effective, overlap capacitance.
Here.
Yes, sir. But in the previous case, we hadn't used the output voltage. Like the same effect can
Very
be
good.
seen in the
Very
previous case, right?
Yeah.
So
Very good.
what may
Very
be
good.
the reason for it?
Very good. Very good. Very good question. Yeah. His point is like while considering this here, we have considered the Miller. Okay. Just to connect this one. Then if you consider this Miller, then there should be one also capacitance of 2 CG not in this input side. Then while we are considering this one input capacitance, we have not considered that. We have just directly added these two. Why so? Okay, very good question. This is just one hint. I want you to be answering this question in the next class. So the hint is, how do you calculate this transition or this propagation delay? What is the funda? Funda is that when we cross the 50% of this total voltage, if this total voltage V, then we can say that when this input or output, when this output changes the 50% of its VDD value, right? And during that time, please do consider what are the region of operations or how these transistors are behaving for this case as well as for this case. Just think it little bit. Um, what is your name?
Rishyendra, sir. Rishyendra.
Rishan. Yeah, Rishan. Please tell me tomorrow. Okay,
Okay,
Rishan.
okay. I will
Okay,
tell you.
think over it. And this is a question to all of you. Please think over it and tell me why we have done it like that. Very good.
So,
Okay. Yeah.
so how are you writing the formula for junction capacitance? Huh? It was like we need to
Junction
consider that
capacitance.
LT as
Junction.
well.
Yeah. Junction capacitance is this one.
Yes, sir.
Huh.
So, sir, how are you writing it as combined as SJPW?
Is
Sorry,
JP.
CJPW in the later section.
Oh, in the later section, it is a combine of all this. Basically, it is this total diffusion capacitance, one for N side and one for the N channel NMOS and the other one for PMOS. So it's basically this plus this, means the bottom part as well as the side capacitance part.
So it will be like total in the C diffusion only, right?
It would be the total C diffusion only. Total C
Yes, sir.
diffusion would be different for N channel as well as P channel.
Yes, so
That's what.
that part I got it. Like
Huh.
you had written there as CJPW. So here it's not completely directly proportional to W.
Okay, here it is not completely
So because
proportional
there is a part
to to
CJSW
W.
to LD as
Okay,
well.
okay, yeah, yeah. I agree with you, because here you are saying that here some 2 LGD part is also there because of that, right?
Yes, sir.
Okay,
Yes.
okay. So maybe then you know 1 minute CJSW, right? 1 minute CJSW, right? So okay, what is this sidewall capacitance? Sidewall capacitance is like one because of this, one because of this, one because of this, right? And you were
Yes.
saying like because of this one, right? This is not dependent on W, as well as similarly for this part, this
Yes, so
is
those
not dependent
green.
on.
Yes.
Right, right, true, true, true. I agree with you. Yeah. So in that context, the reason behind is this is again some approximation here. That is because compared to this width, compared to this width, this value, this LD value is lower. Okay, compared to this width, this diffusion length is or this diffusion region length is lower. So as a result, this other contribution would be more compared to this contribution. So that way, like for the latter case, this part has been type of neglected.
Okay, got it, sir.
Okay, okay, true, right, good, very good observation, very good. Okay, so now let us come to the one situation where like consider the following case. Here you can see one inverter is driving another inverter, and you can see this inverter is been like output node is been driving the input of this next stage inverter. So they may not be like exactly in the side by side in a chip. They may be a bit far apart. So as a result, those wiring capacitance should also come into the picture. So then we have represented this wiring capacitance, okay, or the capacitance because of this connecting wire, right? It will also contribute the capacitance. So this we have written as C wire, right? Then we have to find what is the total capacitance at node 1, right? So what is the total capacitance at node 1? That means when you are considering the propagation delay, then we should know what is the total capacitance at this node 1. This is required to find the propagation delay, right? This is required to find the propagation delay. Yeah. So anyone can help me in this regard. So what should be the total capacitance at this output node? Quickly, I need to cover a little bit more. So it is C. Okay, I can say like C out 1, output node associated at node 1. So it would be the first, the input capacitance, right? Input capacitance of the next stage. So C input capacitance of next stage, right? Plus C wire capacity, this capacitance due to this wiring, plus C self, right? Because of this capacitance which are associated from this inverter 1. So this is associated with inverter 1. This is associated with inverter 2, and this is the wiring capacitance, right? And if you see it, we have explicitly discussed what would be the value of C self for an inverter, what would be the capacitance of, and what would be the input capacitance of an CMOS inverter. So then what would be the total capacitance? The total capacitance would be equal to this. Let me copy it. So the total capacitance would be this. Then the total capacitance would be C wire plus this C self. This one plus C self. So let me take this black color again. So it would be this one plus C wire plus this one. So this is this part. This wire is this part, and this is from this part, right? So if you know, then like what are the widths of these inverters and their respective values are given to you, means numerical values are given to you, then you should be able to find what is the total output capacitance at node 1, and that is required to find the propagation delay, okay, for this first inverter. Similarly, if you want to find the propagation delay for the second, you can do the same analysis to find the for the second one. Maybe for the second one, you are not probably connecting any load, I mean any inverter, but maybe it is driving some another capacitive load. Okay, then we can consider accordingly here, right? Here C in of the next stage would be equal to CL, right? For this case. But similarly, C where if there is some wiring capacitance, it should be considered, as well as C self should be there, right? So the moral is of the story, and which is very fundamental and important in nature, is that you should know when you are considering an inverter or any digital logic, you should also know that the digital circuit will also load itself, right? And if you have a higher load, means higher capacitance, just by only making the previous stage bigger or the width bigger does not help much. Okay, now quickly here one type of small thing. So how do you then estimate the propagation delay, okay, in an CMOS inverter? I think the basic we have already discussed. Just to have a recap, we have two components like TPHL, TPLH, and it's basically given as 0.69 R equivalent of N for this N transistor and this CL. Now, what is the CL? CL is the load capacitance. It does not mean the CL is only this one, only this load capacitance, or only this load here, or only this one. This means C1 is basically this C out. Okay, this is C out in the next page. Okay, so C out is basically C in the next page. So remember that, right? So CL is basically this one, right? When you're considering CL, CL means CL includes everything. Right. So now we know how to find the capacitance, fine. But to estimate the delay, another important parameter or quantity is this R equivalent, right? What are the equipments? What would be the equivalent resistance of an of an transistor, right, when operating? So for that, you can find different techniques. So one of the easy technique is like to do some like approximations, okay, to find the resistance, because you see the resistance is not at all fixed. Here if you consider the resistance in this region, resistance is something. How do you find resistance? It is basically the voltage by like current, right? The bulk means if you consider this, say okay, for example, say this condition, and this is a logic one you have given, so this MOS is off, and this MOS is on, PMOS is off, NMOS is on, and say that this has been charged to VDD. Right now, it has a path through this capacitive load has a path to discharge it through this inverter. Right now, you remember here, this CL does not mean it is the only and fixed load capacitance. It can be an inverter like next stage as well. So in that case, both gate capacitance should discharge, right? If it is the CL means it is another inverter, then both gate capacitance which are initially charged, now they have to be discharged through this MOSFET. Okay. Now how do you estimate? Okay, one approximation for this estimation is you consider, like, for example, this one ID VDS characteristics, ID VDS characteristic, and your characteristic basically looks something like this for an finite value of lambda, right? Then it should have some slope. And how it is actually been done is done actually like that, because propagation delay is propagation delay this propagation delay is this associated with that 50% change, right? Change in magnitude, right? 50% change in magnitude. So as a result, you can say, like, when this output is changing from VDD, okay, to VDD by 2, okay, the resistance between these two, say this is VDD, I just need one more minute, okay. So VDD by 2, then the capacitance, then the resistance, so one resistance is this one resistance is this one, right? So if you can find what is the average resistance between these two, that would basically give you and some way estimation between an average resistance, okay, for this NMOS inverter. Fine. So I hope this part is clear to you, right? Like you can see that this this VD sat or whatever this V sat means, whether it is a small signal, means small short channel MOSFET or long channel MOSFET, depending on that, and more or less compared to this VDD, this region would be pretty small, right? So we can say for most of this VDS, means output transition region, the transistor would be in the saturation region only, right? So you can take an average between these two and find what is the average resistance of this transistor. Same technique you can also do for this PMOS to find the resistance, equivalent resistance of a PMOS transistor. Yeah, I think a little bit more discussion is here regarding the estimation of resistance. I think we can continue it from here in tomorrow's class. Okay. So yeah, then thank you very much. So we'll meet tomorrow, okay, with this. If you have any question. Okay, so if you do not have any question, okay, thank you. Thank you very much for attending, and we'll see you tomorrow. Thank you.